Hi, welcome to the Olympiad geometry. Let's continue our study. Before we start, if you think this video is helpful, please click the like button, comment, share, and subscribe to the channel. So let's continue our study on the 9-point circle. Today we're going to talk about the theorem that relates to the 9-point circle. It's called Coolidge-Ogami theorem. It's saying that to choose any 4 points on circle O, each 3 points forms a triangle. The 9-point circle centers of 4 triangles are cyclic. So the problem is saying that we can find any 4 points on this circle O. And each 3 of the 4 points forms a triangle. Right. So we have triangle ABC, triangle BCD, triangle CDA, and a triangle DAB, right? We have these 4 triangles, and we want to prove that the 9-point circle of these 4 triangles are cyclic. So the easiest way of this problem, because these 4 points are arbitrary, so if we think about the relationship between the 9-point circle and the auxiliary center O, that would be easy, right? Because all of these 4 triangles, they share the same circumcenter, which means that we can find the auxiliary center. We know that the 9-point circle, the center of the 9-point circle V is midpoint of auxiliary center H and circumcenter O, right? And for all of these triangles, they share the same circumcenter. So we can just choose to use a unit circle here. Let's draw the circle first. Right, we have a unit circle here, and we can choose any 4 points. Right? So let's say A is x1, y1, B is x2, y2, C is x3, y3, and D is x4, y4. Right. So we know that VA would be the midpoint of HA and O, right? So the midpoint H, because the coordinate of O is 0, 0, so we just need to find the coordinate of the auxiliary center. And the auxiliary center is easy to find because OH equals to 3 times of OG, right? And we know that centroid G can be calculated. For example, for the triangle ABC would be A1 plus B1, x1 plus x2 plus x3 divided by 3, right? And y1 plus y2 plus y3 divided by 3. That's GA, which means HA, the coordinate of HA is x1 plus x2 plus x3, and y1 plus y2 plus y3. Right. Then we know that VA is, because VAO is half of HAO, so we know that VA coordinate of VA is x1 plus x2 plus x3 divided by 2, and y1 plus y2 plus y3 divided by 2. Right. Now we know the coordinate of the 9-point circle of the triangle. I call it VA. It's actually VABC. Right. We know that this is the coordinate of the center of the 9-point circle of the triangle ABC. And if we just consider just look at this one. This is so symmetrical, right? It's just excludes the fourth point, which means that if we want to make something to prove they are cyclic, we just need to find the center and prove it's on a circle. So it just excludes the fourth point. Similar for the triangle, let's say VBCD, right? The VBCD would be x2 plus x3 plus x4 divided by 2, y2 plus y3 plus y4 divided by 2. Exclude x1, y1, right? So think about the point. Think about the point x1 plus x2 plus x3 plus y plus x4 divided by 2, and y1 plus y2 plus y3 plus y4 divided by 2. Right? Think about this point. Then we can calculate the distance between VABC to this point and VBCD to this point, right? The distance would be x1 plus x2 plus x3 plus x4 divided by 2 minus x1 plus x2 plus x3 divided by 2, right? This one square plus y1 plus y2 plus y3 plus y4 divided by 2 minus y1 plus y2 plus y3 divided by 2 square, and squat. That's a distance, right? So here we got half of x4 square plus half of y4 square and unsquare, right? We got square of this one, so it's a half of x4 square plus y4 square equals 2 half, which means for the distance from VBCD to this point would be half of x1 square plus plus y1 square, which is 0.5, right? So they're equal. Similarly, you can prove that for the VCDA and VDAB, the distance from these 2 points to this point are also 0.5. Okay? So this theorem can actually be extended to like any points, like 5 points or even more. Okay, so this is today's theorem and problem. Maybe you can hear that I'm still sick, so hopefully I can make more video tomorrow. Thank you. See you in next one.